Good morning. Let us start. I hope all of you can hear me. We will continue on our discussion of topic models. Just confirm, are the slides changing? Anybody? Do you see the second slide? Somebody?
Yes.
Yeah, okay, thank you. Okay, so what we are interested in is to given a collection of documents where each document is again a bag of words. We want to attach topics to the documents, and one document is annotated in terms of multiple topics in some proportion. That means you have a number denoting how much that topic is associated with a document. Similarly, every topic is nothing but a collection of words or tokens, again according to some weights. So you have a two-way thing. A document is a collection of topics and a topic is a collection of words. Now the question is, how do we assign these topics to the document, and how do we find which words form a particular topic? There are many applications which we saw, and we in order to do so, we talked about this particular generative model. The model is as follows. So the only thing we observe is a collection of words that form a document. We particularly ignore word order. We just take it as a bag of words. And how we generate document is as follows. We randomly choose a distribution over the topics. So for a document, we randomly choose a topic proportion. Meaning we decide how much of so suppose there are k topics. Basically we select a k dimensional vector where the elements of the vectors are probabilities that that particular topic is present in this document. Okay, so let me write it down. Yeah, so if this is my doc1, and suppose I have topic 1, topic 2, topic 3. Let's say I have only 3 topics. So every document would have a topic proportion. Let's say 0.3, 0.6, and 0.1. Similarly, every document in the collection would have, so you would actually have a matrix which is number of topics k versus number of documents n, or no, number of documents d. Okay, so what we first do is that suppose I want to generate doc1, the words in doc1. According to this probability, I pick up any one particular topic. Say I pick up topic 2. And after I have picked up topic 2, by the way, this distribution of topics over documents, this also I have got from some other distribution. I'll discuss that. This we have got from another distribution itself. So you can think of that if you look over all the documents in the collection, this itself is a distribution over the documents, distribution of this vector, this multidimensional distribution. This itself is a distribution. Maybe there is some kind of complex multivariate distribution over the documents. Okay, so each of these row vectors in this matrix is a sample drawn from that distribution. Okay, suppose I have got this sample, then I toss a coin and then decide which topic has been generated. And now I go to the topic versus words matrix. So I have another matrix which is again like this. So you have topic 1, which is, let me write it this way. So you have topic 1, then topic 2, and topic 3, and I have word 1, word 2, word 3, word 4. And again, I have a vector which says that what is the probability of word 1 belonging to topic 2, what is the probability of word 2 belonging to topic 1, and so on. Okay, so we have again a vector like this. So suppose topic 2 is chosen. What I will do, again, how this vector can also be thought of as a distribution of words over topics. You can also think of it as another distribution. This matrix itself as a distribution. And every row is a sample from that distribution, a point from that distribution. I randomly pick up I go to the point which has been picked up here. Say topic 2 has been picked up. So let's say you find out what probabilities in topic 2. Let's say the what probability is something like this: 0.1, 0.1, 0.7, 0.1. Let's say. So again, I randomly generate a word. Let's say this word is generated. So word 3 will be the one of the word generated in document 1. And I'll repeat this process for capital N number of times if capital N number of words are there in the document. So finally, I get a backup word. And we assume a document is generated by this process. Two observations. First is that these vectors themselves, if we consider the collection of documents, that is the corpus, they themselves represent a distribution. Secondly, or similarly, the words vectors which form a topic, they themselves form a distribution over the collection of topics. So there are total 4 distributions. One distribution, rather 2 high-level distributions, outer loop distributions, and 2 inner loop distributions. Not 2, actually many. So this is one inner loop distribution, this is another inner loop distribution, this is one inner. So this is a collection of distributions. Similarly, here there is a collection of distributions. And these collections themselves are a distribution. So the outer loop distribution is a distribution over distribution, while the inner loop distribution are not one, but many distributions which represent this proportion, topic proportions and word proportions. Also, we have in this generative model, we have assumed that order of the words are not important, which means that each word is generated independently of the other words. So now let us try to write this down in a more formal way. So we'll take help of something called a graphical model or a plate diagram. I have already discussed it earlier in the beginning, but let us discuss it once more. So what on the left you see is a typical graphical model where every node is a random variable. Every node. So this you remember because we will encounter this in much more frequently henceforth. So every node is a random variable, which may be of 2 types. If it is shaded, it's an observed random variable. If it is not shaded, it is either a latent variable or a parameter. Both are unknown. Latent variable is also not observed and parameters are directly not observed, has to be estimated. And shaded variables are the ones that we actually observe. And an arrow between 2 nodes denote direct influences. Okay. So if we draw such a directed acyclic graph, or forget about acyclic, if you draw such a directed graph, it basically represents a factorization of the joint distribution of all the variables. So in this case, I have 4 variables, x1, x2, x3, and y. If you look at the joint distribution of these 4 variables, this diagram, this graph, would basically say that this joint distribution can be factorized. How they can be factorized? They can be factorized as Px1 given y. You look at only the direct dependencies. Px1 given y, Px2 given y, Px3 given y into P of y. You actually see, if there is only a direct dependence like this, you could have done a factorization like this. And this graphical model actually is nothing but a visualization of this factorization. It's just a visualization of this factorization, right? So, so this is what graphical model means. Since often there are large number of variables, large number of random variables in a model, in order to draw a more compact diagram, we do the following. You see that this same structure, y influencing x1, y influencing x2, y influencing x3, are repeated 3 times. So any such repetition is represented in the following way. So instead of writing x1, x2, x3, I just write x, only one x, and I said it because all these 3 are observed, and then I have a direct influence from y to x, and because there is a 3-way replication, I enclose it in a box, in a plate. I enclose it in a plate, and in the bottom of the plate, I write down the number of replications, here 3. So I write down the number of replications 3. So this plate model is nothing but a shorthand for this graphical model, and the graphical model is nothing but a visualization of the factorization of the joint distribution. So I think this is pretty clear. You can write, for example, if I have say something like this, the other way around, and this is okay. So if I had had the other way around, x1, x2, and then y, I could have written it as x with the replication 2, and then y, and then y. I could have also written it like that. So this is the meaning of the plate diagram. You try to remember this because I'll use this henceforth. Okay, so now let us write the generative model that we discussed earlier as a plate diagram or a graphical model. And this generative model is something called a latent Dirichlet allocation. It's called a latent Dirichlet allocation. Let me explain what the process it is. Let us first talk about some notations. So this beta 1k is this matrix, is this matrix. So you have topic 1, topic 2, topic k. You have word 1, word 2, word 3, word 4. Okay, so let's say beta I is nothing but the distribution of topic I in terms of the words. So this vector is say 0.1, 0.1, 0.6, 0.2. This vector is beta I vector. This represents its size is the size of the vocabulary, and it represents the the probability of the jth word. So beta ij would be probability of the jth word being belonging to topic I. Okay, so this is the first quantity. Second quantity is the topic proportion for document D. Okay, so you have another matrix. So you have two important one. Another is the theta matrix. So theta matrix is like this. You have document 1, document 2 up to document D. And you have topic 1, topic 2 up to topic K. Okay, so theta D is the document, dth document, in what proportion, say 0.7, 0.1, 0.1, 0.1. In what proportion are the topics present in document D? Is the topic present in document D? So this is the theta. Theta. So these two you keep important. Theta is called the proportion matrix. And beta is called the topic matrix, or sometimes the topic word matrix. Topic word matrix. Right. These two are most important. Note that I have written this as a matrix, but every row of this matrix, it can be considered as a distribution. In the first case, beta case, it can be considered as if the vocabulary size is V, it can be seen as a V valued distribution. And similarly, if you look at the topic, it can be seen as a K valued distribution. So every row represents a distribution. So every row is like let's take beta. So if capital V is the number of words, you can think of every row as a V-faced dice, where the values 0.1, 0.6, they represent the bias or the probability of each face of this V-faced dice. And if you throw this dice, what will be the outcome? One word will come up. One face will come up. A face is a word. Similarly, in the proportion matrix, it is a K-faced dice. And not one, it is a set of K-faces dice, one for each row. And every row represents what are the biases of that dth dice. The biases of the dth dice is say 0.7 for topic 1, 0.1 for topic 2, and so on. Again, if you throw this dice, one particular topic will come up. So the topic that comes up after throwing the dth dice, if you throw the dth dice, one particular topic will come up, is one integer will come up, let's say, that is ZD. That is ZD. Okay. That is ZD. And what is ZDN? Is that this is the so ZD is a particular topic for assigned to document D, and ZDN is the if you so now we have got a topic, and now we have generated a word, so you can assume that what has come from that topic. So go to the D8 document, look at the generation of the nth word. Before the generation of the nth word, some ZD was generated. So you say ZDN belongs to that ZD. It's the topic for ZD. Okay. And finally, WD, the collection of observed words. in the document D. It's the bag of word of document D. Okay, so it's the outcome of a set of trials to generate the words in the above generative process. So with this notation, let us write down the plate diagram. So let me explain what it is. So you see this beta, if you remember, this beta is this topic word distribution. Beta is this topic versus word distribution. Or let me do it. See, finally, what we are generating? We are generating the nth word. Let us first look at the random variables. Okay, so the only observed random variable in this process is this word. Okay, so this word is the nth word of the D8 document, that is a single word. So that's how we represent. All right, so nth word of the D8 document. And what are the other random variables? So this is the observed random variable. Other random variable, this is the topic, one of the topic which is assigned to document D, and this document, this topic has been generated by from a topic distribution. So ZDN is the topic associated with the nth word in document D. Is a topic associated with the nth word in document D. I'll explain with an example, but you imagine. So this is another variable. So this is basically, if you have the D8 document, D8 doc, and you look at the nth word, So first, what you remember the generative process? First, I attach a topic with the nth word, and then from the word distribution of the topic, I generate a word. So whatever topic I assign, say topic 2 or whichever integer I assign, that is ZDN. And you can see, because directly WDN is determined once ZDN is decided, so it is conditional on ZDN. So there is a direct influence of ZDN and WDN, because what topic you choose depends on what you generate. So that's why this arrow between ZDN and WDN. And you see this plate, it means that this topic, first you generate, then you generate a word. This is repeated capital N number of times, where capital N is the number of words in a document. It's the number of words in a document, right? So this is a plate in replication. All right, but generation of word is not just decided by which topic I choose to generate it from. It's not just decided by which topic I choose to generate it from. Along with that, it is also decided by the word distribution over the JDN topic. It is also decided by the word distribution of this particular. For example, let's say this. I say the from this distribution or whatever. As I go outside, go towards. As we expand this plate diagram, I'll see. Let's say the topic for the 10th word of the first document, I decide the topic that I should use for this is, let's say, sports. And so ZDN would be sports, WDN would be 10th word. But just knowing that it is decided, it is generated from sports is not enough. We have to look at the distribution of words in the sports topic. And that is given by the vector beta. So the beta is, say, cricket 0.9, football 0.1, and say hockey 0. Okay, so this is, say, beta for the sports topic. Okay, so once I decided that ZDN is sports, I will go to this beta distribution, which is cricket 0.9, football 0.1, hockey 0. And then I generate a word most probably the word will be cricket, so WDN will be cricket. So this distribution beta also influences my WDN. It also, because if this distribution was something else, if it was cricket 0, football 0.95 and hockey 0.05, this would have been different word. Okay, so beta also decides. So I draw this arrow, beta decides. And that again is replicated n times. So I have every word is influenced by beta. So I have a plate n replicated plate. Okay. So now let us look at how this Z is generated. As I said before, Z is one particular topic, say sports. How is Z generated? We look at the topic. We are still talking about doc1. We have a topic proportion. Let's say topic proportion for doc1 is 0.8 sports, 0.1 politics, and 0.1 science. 0.8 sports point. So that is my theta for theta1, theta for doc1. All right. And this sports topic that I decided is decided by this topic proportion. It's a sample drawn from this topic proportion, which is 0.8 sports, 0.1 politics, 0.1 science. This is my theta for doc1, theta d, or theta1. So that's why there is an arrow, but note that this topic proportion itself is a random vector, because it changes from doc1 to doc2 to doc3. It itself is a random vector. It itself, we don't know what it is. It's a random vector and it is unknown. But this will determine that the sports topic has been drawn according to this proportion. So theta d is the part document topic proportion for the dn document, and that influences zdn. And now you see this influence that theta d produces zdn. This is again done for every document in the corpus, every capital D document in the corpus. So this is a replication capital D types. So that's why I have this plate. Now what I say is that this theta, this part document topic proportion, theta1, theta2, theta3, each of them are vectors. Each of them are three-dimensional vectors if we have three topics. So this capital D number of three-dimensional vectors, this theta d, we can think of them as capital D samples. Capital D samples, where each sample is a vector. Capital D samples drawn from some distribution. Drawn from some distribution, which I call, say, the outer loop distribution, drawn from that distribution. And alpha is a parameter of the distribution. Let's say the variance of the distribution or mean of the distribution or something. How are the topics distributed over documents? That's a corpus property. That is a corpus property. Okay, it's a property of the corpus. So alpha is a parameter. Alpha is not a latent variable. Alpha is a parameter. And that determines what my theta d collection would be. And this is replicated over the corpus, so it's inside the plate. Now look at the word distributions. So beta 1 is the word distribution. Say I have 4 words, cricket, hockey, soccer, and say badminton. So I have 4 words. Say the topic 1 is say IPL. It will have cricket 0.9 and football 0.1 and others 0, let's say. So that is my vector, beta 1 vector for topic 1. Similarly, I have beta 2 up to beta k. So that's why this plate k, where k is the total number of topics. So now again, these vectors beta 1, beta 2, beta k, they themselves can be thought of as a collection of distributions, as a collection of samples drawn from another distribution. So this is the what topic distribution. It's a across the topics, and that IPL is 0.9.100. Who decides that? And similarly, if we take European Premier English Premier League EPL, that is another topic distribution. That is another word distribution. Say for soccer there is 1 and rest are 0. So this way you get several topic versus word vectors distributions, and each of these vectors can be thought of as drawn from some other distribution, which is called the topic parameter. And let's say eta is the parameter for that distribution. So eta decides beta k as a parameter. Similarly, alpha decides theta d as a parameter. So that completes the plate diagram. Any question you can ask? Okay, so now since this is basically a graphical model, I can write down the factorization. I can write down the factorization for I can write down the factorization for P alpha theta d z d n w d n beta k eta. This entire joint distribution I can factorize this way. Let's say basically we look at the direct influences. So only thing on which we have a 2 influence is ZDN on WDN and beta k on WDN. So let's do that. So this is a product because there are n replications for and they are independent. Every word is independently generated. So it is PZDN given theta d. So this thing PZDN given theta d into PW. So it has 2 factors. One is this factor and the other is this factor. Okay, PWDN given beta and ZDN, because both parents have to be taken for this. Both parents have to be taken. So this is how you generate WDN, and you are doing it n times because the plate is of replication n. So it's product 1 to n, assuming they are independent. And now let us look at theta t. So theta t has only one parent, alpha. So it is P theta d given alpha, and this again is a dereplicated plate, and every document is independent of other. So I have a product d times. So this is P. This is another factor. So this takes care of this edge, this link. And finally, we have one link left with this link. So this is P beta I given eta. And this is a product over, or this is a k replication. So it is a product over k, assuming each topic is independent of the other. This is a little more restrictive assumption that every topic is independent of other, but anyway, let us do it. So we multiply, get this. Okay, so this is the final factorization as denoted by this plate diagram based on our assumption. So you see that now given this plate diagram and given this factorization, so when we decided this Leclerc-Dirichlet allocation or this topic model, our generative model, as we visualized it, is captured in this factorization or in this plate diagram. This is only the structural part of the model. We have decided the structure of our generative model. Now we have to assign some distribution to each of these probabilities, some functional form of the distribution to each of these probabilities. So you see there are 4 probabilities. Okay, we have to there are 4 probabilities. So we have to assume some distributions for these 4 probabilities. In LDA, we assume these distributions to be as follows. So what is, let us look at, so what is P Zn Zdn given theta d? Let's see. So what is theta d? Theta d, we remember, is the topic proportion. So theta d is the topic proportion for document D. So it will be like this. So I have topics T1, T2, T3 up to Tk. And the topic proportion of document D is, let's say, 0.1, 0.1, 0.1, 0.2. This is given. In this particular probability, this is given, that this distribution 0.1, 0.1, 0.2 is given. What is Zdn? Zdn is an integer. It is one particular topic drawn according to this distribution. That means you imagine theta d again as a k-faced dice, with 0.1, 0.1, this being the bias of each face. If we throw these dice, one integer will come up. Say the third face has come up, T3 has come up. So this Zdn is nothing but that outcome. Zdn is nothing but that outcome. That if you throw a dice, which integer comes up? So that is my P. So what is the natural distribution for this? The natural distribution for this is the multinomial. So multinomial, you know, it's the extension of the binomial, or the Bernoulli rather. It's not multinomial, it's called multinomial. It's the Bernoulli. What's the Bernoulli? It's the coin toss. You toss a coin, head comes or tail comes. So the outcome is 0 or 1. And what are the parameters? Parameter is P, the probability of head coming, or 1 minus P, the probability of tail coming. So P and 1 minus P. This is the Bernoulli distribution. Here we extend it. Instead of 0, 1, we have 1, 2, 3, 4 up to k outcomes. And the probability of these outcomes are theta 1, theta 2, no, not theta 1, theta 2, 0.1, 0.1, 0.2, something like this, which add up to 1, which adds up to 1. Just like P and 1 minus P adds up to 1. And so the natural distribution for this is the multinomial, or sometimes called a categorical or a discrete distribution. It's like there are k categories and the probability of each category is something. If you randomly choose a category, according to this probability, which category you will choose? That's the categorical or the multinomial distribution. So this is multinomial. Similarly, what is PWN given beta and Zdn? Let's see. So suppose Zdn I have picked up to be, say, 3, the topic 3, topic number 3. So now topic number 3, let us look at, it has a word distribution. Topic 3, it has a word distribution. Say word 1, word 2, word 3, word 4 up to word V. Okay, let's say the word distributions are 0.1, 0.1, 0.2, 0.3, and so on. Okay, so given this, so these vectors, this is my beta 3, the word distribution. Remember the beta, this beta. This beta. This is the word distribution for the third topic. Third topic, what is third topic? Third topic is nothing but, because it is the third topic, because Zdn was 3. Zdn was 3. Okay, so given Zdn equal to 3, this beta 1 to k is this. Beta 1 to k is this. So now what is Wdn? What is Wdn? Again, it is a V-faced dice with probabilities 0.1, 0.1, 0.2, 0.3 for each face. You throw the dice, one of the words come up. Say the 100th word come up, W100 comes up. Okay, so this is also a multinomial distribution. similar as the previous. This is also a multinolly distribution or a categorical distribution. Okay, similar. Only earlier thing was k facet. This is v facet dice with this beta probabilities for each phase, beta vector. Okay, so this is also a multinolly. Okay, so two distributions we have decided. Now let us look at the other two distributions. So what is p theta d given alpha? That means what is the probability that document D has this theta vector, has this topic proportion? What is the probability that document D has this topic proportion vector? It could have something else. It could have 0.9, 0.1, 0, 0, 0. It could have 0.5, 0.4, 0.1, 0, 0, 0. Some other theta D could have been given to document D. Some other topic proportion could have been there. Okay. So let's say this theta D is generated as a sample from some other distribution. As a sample from there, some other distribution whose parameter is alpha. Whose parameter is alpha. Okay. So what type of distribution that would be? So somehow our mental process is like this. I have a distribution over vectors theta d, distribution over vectors theta d, where the elements of the vector are 0.1, 0.1 like this type, such that they add up to 1. And from this distribution whose parameter is alpha, I pick up one particular vector theta d and use that in the multinomial. Use that as my multinolly probabilities. Use that as my multinolly probabilities. So this distribution, because note that if each theta d vector itself is a distribution, itself is a multinolly distribution. Okay, so this alpha distribution, let's call it alpha distribution. So this alpha distribution is a distribution because a sample from alpha is a multinolly distribution. A sample from alpha is a multinolly distribution in this vector. Each vector is a multinolly distribution, theta vector. So this alpha distribution is a distribution over multinolly distributions. It's a distribution over distribution. It's a distribution over multinolly distribution. Similarly, beta is a multinolly distribution. So this eta distribution, it is also a distribution over multinolly distribution, similar way. And the most common distribution used for this purpose, just like Gaussian is used for most purpose and exponential distributions are used in many purposes, the most common distribution over multinolly distribution is something called a Dirichlet distribution. We'll explain it in detail soon. It's called a Dirichlet distribution. Okay, so we assume these two distributions to be Dirichlet with parameter eta. I'll explain the what parameters mean, and this is Dirichlet with parameter alpha. So now I have all the four distributions. Okay, so these are the two types of distribution we'll use: two multinomials and two Dirichlet for the each parts. Okay, so next I will explain the multinolly. I think is clear. It's nothing but a k-facet dice. I'll explain in more detail the Dirichlet distribution. Let me take a quick break. And I will come back. It's 8:54.